information valuable to us, and how do we find these values for different materials? So the answer to that is there's an experimental procedure that is used to determine the amount of energy transferred from one substance to another is heat. So we can find out how much energy is transferred between two objects. Okay, so this would be the energy as they reach thermal equilibrium. And this experiment allows someone to find the specific heat capacity of a substance. And what this is called calorimetry. So calorimetry is this procedure, this process, and it is an experiment. And in fact, it's an experiment that you will have a chance to do in lab a little bit later. So what is calorimetry? Okay, well, in calorimetry, you need to use something called a calorimeter, which is what you see pictured here. This is a calorimeter. You've got some container, and it's insulated very well from the outside, so there's no heat transfer in and out of this whole device. Okay, then you have another device in here, okay, and you use some wires or something to burn it so that all the energy in that substance can be transferred into the water. Then you have this stirrer here that stirs the water so that the energy transferred right outside of it ends up being mixed around so that you can see the change in the thermometer here. And based on that change in temperature, our good old friend here, delta T, it will tell you how much energy has been lost or gained. So water's specific heat is well known, okay, so this is the CP of water, I'm going to write it CPW, is well known to be 4,186 joules per kilogram degree Celsius. You don't have to memorize this, but this is going to be a number you become familiar with. Okay? An assumption that's made is all the heat of this material is transferred to the water. Okay? So all heat is transferred. Okay? And what this does is then we get that delta T, right? So we can use our equation to find out what has happened. So if all this heat is transferred, what we get is that the change in energy of the water, which is a positive change, will be equal to the change in energy of whatever our substance is. So I'm calling it X. So this one needs to be negative because it's energy lost, so it's a negative value. Okay, and heat is being added to the water, so that will be a positive value. So now using this, okay, we can take this equation and using our equation for specific heat capacity and using our equation, rewriting it this way in terms of Q, we can set it up so that if QW equals negative QX, we can rewrite it plugging these in so that we have CPW, so our specific heat capacity of water, the mass of the water, and the change in temperature of the water will equal the negative change, and I'm going to run out of room here, so actually I'm going to write this down below. So let's go equals the negative specific heat capacity of whatever our other material is times the mass of that material times the change in temperature of that material. And we can use that then if we know all the changes in temperature, all the masses, then we only have this final minus initial temperature, and we can find how much heat was transferred between the two objects. So now, let's look at an example of using this to solve for some fact in these two equations. Okay, we want to know something that's going to happen. So our example here is we're going to ask this question: what is the final temperature when a 3 kilogram gold bar at 99 degrees Celsius is dropped into 0.22 kilograms of water at 25 degrees Celsius? So we're going to take one of these pretty gold bars, dump them in some water, find out what happens, and we're going to calculate the final temperature. So we're finding TF. Okay. I want you to notice that they will need to reach thermal equilibrium. So remember, thermal equilibrium means that they're at the same temperature. Okay, so since they're at the same temperature, TF will be the same for both materials. But as you can see from the question, they don't start at the same temperature. So this is our temperature initial for gold. And this one here is our temperature initial for water. Okay? Then if you remember, we also need to know the specific heat capacity. So the specific heat capacity of gold, you'll always be given that information if you need it and you aren't trying to solve for it. So in this case, the specific heat capacity of gold is 129 joules per kilogram degree Celsius. And we remember from before that the specific heat capacity of water is 4,186 joules per kilogram degree Celsius. So I want us to pause here and looking at these two specific heat capacities in our example earlier with glass and ice, what is the final temperature going to be closer to? Is it going to be closer to the 99 degrees of the gold or the 25 degrees of the water? Okay. Well, because water's specific heat capacity is so much greater, okay, so the CP of water is much greater than the CP of gold. That tells us that our final temperature will be closer, okay, to the initial temperature of water. Sorry for the bell starting to ring there. I had to pause it. But now this helps us answer or know if our answer makes sense and if we did it correctly. Okay, so that's always a good thing you want to check when you're doing problems is, does your answer make sense? So now that we've taken a look at this, we're going to hope we get an answer closer to 25 than to 99. And if so, we know our answer makes sense and we probably did it right. So we don't want to forget our mass of 22 kilograms of water and 3 grams of gold. And I'm going to go ahead and move on to another slide so we have time to work out the problems in this question. So I took the time to already write out all of our variables and write out the equation. And now we're going to look at how to put this all together to solve for the final temperature. So we start with our equation of Q equals CPm delta T. Okay. And now what we need to do is we need to look at the Q of the water and the Q of the gold and think about which way things are going. So what's happening is the Q of our gold, it's going to transfer heat to the water because it is at a higher temperature and heat always goes from high to low. So what that means is our gold is losing energy, and because our gold is losing energy, we're going to give it the negative sign. Now that we've given it the negative sign, what we need to do is to plug in using this and using the fact that delta T is our final temperature minus our initial temperature. So let's rewrite this out now. So Q of water becomes the CP of water times the mass of water. Now times our final temperature, which is the same for both, minus our initial temperature of water. And that will equal our negative. It's a nice negative sign there. There we go. Negative CP for gold times the mass of our gold. And now our change in temperature will be the final temperature minus our initial temperature of the gold. Now, for those of you who like to maybe solve for temperature final, this is a little bit of a difficult problem to do, and I find it easier to plug in all the numbers, calculate them, and then solve for temperature final because we have it on both sides of the equation. So if you struggle with this in class, be sure to ask me so I can help you with the math because it's just a little bit more confusing than normal. So now what we're going to do is we're going to plug in the values, and I'm going to change my pen color here. So I've got the CP of water, which is 4,186, and I'm going to leave out the units because otherwise I'm going to run out of room. And whoops, I wrote 9, so let's see if I can write 6 there. Okay, so 4,186 times our mass of water still, so that's 0.22 kilograms. Please just ignore that bell. And now we have that times our temperature final, which is our variable, minus our initial temperature of the water, which is 25 degrees Celsius. Now I do the same thing on the other side, and I have this negative sign here, and I have 129 as our specific heat capacity of gold that I plug in. Our mass of gold is 3 kilograms, so I'm going to multiply that by 3. Then we multiply by the final temperature minus our initial temperature of 99 degrees. And now we can start solving the problem. So what I'm going to do here is I'm going to multiply these out times the F and times the minus 25. These two times F times the minus 99, and I'm just going to write out those numbers here for you. So those numbers end up being 900 here. I almost wrote negative, but it's 920.92 TF minus 23,023. And that will equal, here we're going to end up with a negative, so we get negative 387 TF. And then I have a negative times a negative, so it ends up being plus our next value of 38313. Now the best way to solve this is we need to get our t's on the same side. So what I'm going to do here is I'm going to plus 387 TF on both sides. And then I'm going to add this number over to the other side. So I'll plus 23023 to both sides. And so we end up canceling this out and canceling that out. And if I add these and add these, it gives us our final equation. Okay, so here we end up with 1307.92 TF will equal 61,336, which just allows us to now solve for TF, and our temperature final is 46.89 degrees Celsius. Okay. Now, if we look at our initial temperatures, we had 99 for the gold, and we had 25 for the water, and we said it should be closer to 25. Well, that's only a difference of 21 degrees, whereas here we have a difference of 45 degrees. I think I did that wrong. It should be 35. Well, whatever. Either way, it's closer to our 25 value here. So we did indeed do it correctly, and we now have the final temperature when we put a piece of gold into some water. You guys will have a chance to practice this in class. I know that probably felt a little bit long, and it's might even still be confusing. So if you have questions, please ask me. Please write them down, and we will do plenty of practice so that you can understand and do it too. I will see you guys in part B when we talk about heating curves.